This is Ken Willis of Cadence Design Systems, and this demonstration will cover BER analysis for DDR4 interfaces using SystemSI. The DDR4 JEDEC specification introduced a new compliance requirement where you need to evaluate the data bus based on the DQ mask. This requires some advanced post-processing, but more significantly, signifies a shift in DDR compliance from traditional setup and hold timing measurements to designing for a bit error rate or BER target. While BER analysis may be new for DDR interfaces, it's been commonly applied to multi-gigabit serial links for a number of years. This involves statistically post-processing an I distribution in order to produce bathtub curves. In order to get an I distribution of sufficient sample size, channel simulation is required, which enables you to simulate hundreds of thousands or even millions of bits. Channel simulation techniques also enable deterministic and random jitter and noise injection, as well as AMI modeling for equalization effects. Let's take a look at an example. This topology is for a DDR4 byte lane running at 2.4 gigabits per second. We have an IBIS model for the controller, a model from extract.im for the package, a lossy coupled W element for the PCB, a SPICE subcircuit for the connector, and a broadband SPICE subcircuit for the DIMM card from S parameters originally extracted with PowerSI. And an IBIS model for the memory completes the topology. The channel simulator is fully integrated into SystemSI parallel bus analysis. You can access its controls from the analysis options form, and to utilize it, you simply check the box that says Use Channel Simulator for Data Bus Write. This gives you an additional tab in this form for Data Bus Write, where you'll see a number of settings you'll be familiar with if you've used the SystemSI serial link analysis tool in the past. Here, the number of bits to simulate is 100,000 in this case. You can see the BER floor is 1e to the minus 20, and we have 128 bits set up for display as raw waveforms, and the target BER is set up here for 1e to the minus 16. Only a subset of the raw waveforms are typically saved just for disk space reasons. To inject jitter and noise associated with the strobe, click on the controller and click on the Strobe Jitter and Noise tab, where you can save all the different subcomponents of deterministic or random jitter. These impairments will be incorporated into the stimulus bit stream that's provided to the drivers at the controller. Similarly, we can inject jitter and noise associated with the data signals by clicking on the memory components. Here you can set random and deterministic jitter and noise, where these impairments will be post-processed into the I distribution after simulation. Once we're all set up, simply click the play button to kick off the simulation. Once the simulation completes, we can take a look at the raw waveforms. In this case, we had decided to write out the last 128 bits of the simulation, which you can see here. You can look at an I diagram or split the screen between I and raw waveforms. We can also generate a report from here for either the DQ mask or the BER analysis. There are a number of other outputs we can look at in this window. For example, the ramp response that came from the SPICE-based characterization that was initially run. Here you can see the ramp responses of all the signals. This is from a bus level characterization that includes coupling and SSO effects. We can also look at the impulse responses, which are mathematically derived from the ramp responses. These will look a little bit messier than what you're used to seeing in serial link impulse responses, but single-ended coupled parallel bus topologies are simply not as pristine as point-to-point differential pairs. We can also take a look at the I contours, which are derived from the full 100,000 bit simulation in this case, and trace out the innermost I and the outermost envelope for each of the signals. Next, we'll look at the I density plots, which essentially show you the sampling distributions across the I. This is available for each signal. You can also scale the probability density up or down, and you can also grab and rotate the display as you wish. These I distributions are automatically post-processed to generate the bathtub curves that we use to evaluate BER performance. These are the jitter bathtubs, which look at I width versus BER. And you can see that some signals are definitely better than others in this regard. We can also look at the noise bathtub, which does a similar thing, but instead of the eye width, looks at the eye height as a function of bit error rate. All the measurements from the various bathtubs are taken and automatically put into this report. The eye contour measurements are included here, as well as the BER measurements. Here you can see the measurements for the jitter bathtub, where the eye width for each BER is recorded. Likewise, below we can see the same thing for the noise bathtub, where we're looking at eye height versus BER. Comparing the eye width and eye height here at the target BER versus the JEDEC requirements will tell you if you have JEDEC compliance or not for DDR4. Another capability we gain here by virtue of the channel simulator integration is support for algorithmic modeling, or AMI. Here we'll right-click on the controller block and add an algorithmic model to it. This will represent the equalization functionality in the controller, which is typically FFE, or feed-forward equalization. Clicking on the different AMI parameters allow you to adjust their values. For example, this is the number of FFE taps, and this parameter is the number of precursor taps. Subsequent channel simulations will include these FFE effects in the result. The well-behaved nature of DDR4 IOs that run at multi-gigabit speeds means that they lend themselves very nicely to impulse response characterization and channel simulation techniques. Here's a comparison of channel simulation and circuit simulation results for this topology. Here are the same results displayed in iDiagram format. As you can see here, they're nearly indistinguishable. This is typical of what we've seen for DDR4 applications. DDR4 signals a shift in JEDEC standards from traditional setup and hold timing to eye mask compliance techniques, with the idea of a target bit error rate, or BER. Cadence's SystemSI addresses these challenges by applying channel simulation techniques previously used in serial link applications to DDR4 interfaces. This provides a huge simulation performance speedup and the ability to run hundreds of thousands or even millions of bits. This enables efficient jitter and noise injection, as well as bathtub curve generation for BER analysis. IBIS AMI models can also be applied to model controller equalization. Circuit and channel simulations have shown to correlate very closely for DDR4 applications, including non-ideal power effects. The bottom line is that bit error rate, or BER analysis, can now be automatically performed on your DDR4 interfaces. For more information on SystemSI or any other Cadence product, please contact your local Cadence sales team or your Cadence channel partner in your region. You can also visit www.cadence.com. That concludes this demonstration. Thanks for watching.